AP Chemistry Summer Assignment, Part 3, Stoichiometry Problems, Worksheet number 3. Question number 1 is a percent by mass problem. Find the mass percent of nitrogen in each of the following compounds. A. Nitrogen monoxide. To find percent nitrogen by mass in nitrogen monoxide, use the following formula. Percent mass is equal to the mass of the element, the part, divided by the mass of the compound, the whole, and multiplied by 100. To determine the percent nitrogen in nitrogen monoxide, take the mass of nitrogen and divide it by the mass of nitrogen monoxide. Take this fraction and multiply by 100 to turn it into a percent. Substituting in 14.01 grams per mole for the mass of nitrogen and 30.01 grams per mole for the mass of nitrogen monoxide, and multiplying by 100%, you end up with 46.68% nitrogen. Don't forget to round your number to the proper number of sig figs. Both 14.01 and 30.01 have 4 significant figures, so your answer should also have 4 significant figures. Problems B, C, and D are solved in the same way. Try them on your own and come back and check your answers when you're done. Percent nitrogen in nitrogen dioxide should have worked out to be 30.45% nitrogen. Percent nitrogen in dinitrogen tetroxide should have worked out to be 30.45% nitrogen. And the percent nitrogen in dinitrogen monoxide should have been 63.65% nitrogen. Another type of problem that I would like you to handle before coming into class is finding empirical molecular formulas. Use problem 2 as an example of how to handle empirical and molecular formula problems. Benzene contains only carbon and hydrogen and has a molar mass of 78.1 grams per mole. Analysis shows the compound to be 7.74% hydrogen by mass. Find the empirical and molecular formulas of benzene. The first step is to take what you're given in the problem and find the number of moles of each element in the compound. The given is 7.74% hydrogen by mass, which means 92.26% must be carbon. If we assume that we have a 100 gram sample of this compound, then 7.74% hydrogen would be 7.74 grams of hydrogen. The same would be true for carbon. 92.26% carbon is 92.26 grams of carbon. Using the molar mass, convert each of these to the number of moles. The next step is to find the ratios between carbon and hydrogen. Here we find that for every 1 carbon, there's 1 hydrogen. And then use that information from the ratios to write your empirical formula. 1 carbon atom for every 1 hydrogen atom is found in the empirical, or the simplest, formula. You can find the molecular formula from the empirical formula if the molar mass is known. In other words, we need to know how many times to multiply the empirical formula by to come up with the molecular formula. This factor X is calculated using the following formula. Take the molar mass given in the problem and divide it by the empirical mass. The molar mass given in this problem is 78.1 grams per mole. The empirical mass, which is the molar mass of the empirical formula, 1 carbon plus the mass of 1 hydrogen, is 13.0 grams per mole. This ratio always breaks down to a whole number, in this case 6. So if X is equal to 6, that means we have to multiply through the parentheses of our empirical formula by 6. So the empirical formula for benzene, CH, translates to a molecular formula of C6H6. In other words, every 1 molecule of benzene has 6 carbon atoms and 6 hydrogen atoms. Calcium carbonate decomposes upon heating, producing calcium oxide and carbon dioxide gas. Write a balanced equation for this reaction. This is a decomposition reaction. Calcium carbonate, when heated, forms calcium oxide and carbon dioxide gas. Don't forget the rules for predicting products of decomposition reactions. For example, carbonates are known to break down into an oxide, in this case calcium oxide, and carbon dioxide gas. How many grams of calcium oxide will be produced after 12.25 grams of calcium carbonate is completely decomposed? The goal of a stoichiometry problem is to take what's given in the problem, 12.25 grams of calcium carbonate and find a set of conversion factors which will lead you to the answer required, in this case grams of calcium oxide. If you set up your problem correctly, you should have come up with an answer of 6.864 grams of calcium oxide as your answer. Don't forget to use rounding rules to round your answer to the proper number of sig figs. 12.25 has 4 sig figs, and so does 56.08. Your answer should be rounded to least number of sig figs, which is 4. What volume of carbon dioxide gas is produced from this amount of calcium carbonate at STP? Remember, at STP, 1 mole of any gas has a volume of 22.4 liters. Once again, starting with 12.25 grams of calcium carbonate, find a set of equalities which can be used as conversion factors to arrive at your final answer. The correct answer for this one, rounded to 4 sig figs, should be 2.742 liters of carbon dioxide. Hydrogen gas and bromine gas react to form hydrogen bromide gas. Write the balance equation for this reaction. The balance equation looks like this. 1 mole of H2 reacts with 1 mole of Br2 to form 2 moles of HBr. Notice that there are 2 starting points in the second part of this problem. We're starting with 3.2 grams of hydrogen and 7.2 grams of bromine. If you have more than one starting point, it's an indication that you have a limiting reactant problem. And one strategy to solving a limiting reactant problem is to try both starting points to calculate how many moles of product could be produced. So when you have 2 starting points, try them both. In other words, how much hydrogen bromide gas can be produced from 3.2 grams of hydrogen? And then calculate how much hydrogen bromide gas can be produced from 9.5 grams of bromine. 3.2 grams of hydrogen gas produces 3.2 moles of hydrogen bromide, and 9.5 grams of bromine produces 0.12 moles of hydrogen bromide. These answers can't both be right. The one that produces the lower amount of product, the lesser of the two, is the theoretical yield. In theory, when you start with 3.2 grams of hydrogen and 7.2 grams of bromine in this reaction, in theory, you will produce 0.12 moles of hydrogen bromide. That makes the 9.5 grams of bromine the limiting reactant in this reaction. In other words, once 0.12 moles of hydrogen bromide is produced, you will run out of bromine. That makes the 3.2 grams of hydrogen the excess reactant. In other words, when the 0.12 moles of hydrogen bromide is produced, all of the 9.5 grams of bromine will be consumed, but there will still be some of the 3.2 grams of hydrogen left over in excess. And there is no name for the 3.2 moles of hydrogen bromide that could have been produced had we not run out of the 9.5 grams of bromine. We will never make 3.2 moles of hydrogen bromide because as soon as 0.12 moles of hydrogen bromide is made, the reaction will stop. And it will stop because we run out of bromine, the limiting reactant. So how many grams of hydrogen bromide gas can be produced using the amounts in B? Well, we calculated the theoretical yield to be 0.12 moles of hydrogen bromide. We just have to change that number of moles in the number of grams to meet the requirements of this particular problem. 0.12 moles of hydrogen bromide translates into 9.7 grams of hydrogen bromide. How many grams of excess reactant is left unreacted? Well, if we compare how many moles of HBr could have been produced to the number of moles that actually had been produced, we would find that there was a difference of 3.1 moles of HBr, hydrogen bromide, as lost potential product. We can take that 3.1 moles of HBr that could not be made and use stoichiometry to change that into number of grams of H2, the excess reactant in this problem. It works out that 3.1 moles of HBr that could not be produced translates to 3.1 grams of excess H2 left over after the reaction has stopped. So 3.1 grams of hydrogen, the excess reactant, is left over after 0.12 moles of hydrogen bromide is produced. What volume of hydrogen bromide measured at STP is produced? The theoretical yield for this reaction under these circumstances is 0.12 moles of hydrogen bromide gas. Using the conversion factor, that 1 mole of any gas, including hydrogen bromide, has a volume of 22.4 liters at STP, results in an answer of 2.7 liters of hydrogen bromide gas being produced. Try answering the next problem on your own and come back and check your answer once you have it. When ammonia gas, oxygen gas, and methane gas are combined, the products are hydrogen cyanide gas and water. First, write the balance equation for this reaction. This is a very nasty equation to actually have to balance, but this is the correct answer for this problem. 2 ammonia plus 3 oxygen gas plus 2 methane gas produces 2 hydrogen cyanide gas and 6 water. These equations balance relatively easily. However, there are times when you have to call on your knowledge of chemistry to find a unique strategy to balance an equation. To balance this equation, I drew out the Lewis structures for each of the compounds listed, and then using the components of the reactants, I tried to make as many water molecules as I possibly could. I could make 3 water molecules for every 1 molecule of hydrogen cyanide produced. So to make 1 hydrogen cyanide molecule and 3 water molecules required 1 methane molecule, 1 ammonia molecule, and 1.5 oxygen molecules, or in other words, 3/2 oxygen. Multiplying this entire equation by 2 to get rid of the fraction, my balanced equation turned out to be 2 ammonia plus 3 oxygen plus 2 methane produces 2 hydrogen cyanide and 6 water molecules. Calculate the mass of each product produced when 225 grams of oxygen gas is reacted with an excess of the other 2 reactants. The words excess with the other 2 reactants is telling us that oxygen is the limiting reactant. We do not have to concern ourselves with the amount of ammonia or methane in this problem because we're going to run out of oxygen first. But we do have to calculate the masses of 2 products. So starting with 225 grams of oxygen, using the correct sequence of conversion factors works out to be 127 grams of hydrogen cyanide produced. And starting again with 225 grams of oxygen, using the proper sequence of conversion factors works out to be 253 grams of water being produced. If the actual yield of the experiment is 105 grams of hydrogen cyanide, calculate the percent yield. Percent yield is calculated by taking the actual yield, in this case 105 grams of hydrogen cyanide was actually produced, and divide that by the theoretical yield of hydrogen cyanide produced, which in this case was 127 grams. The 105 grams that was actually produced in this experiment divided by the amount that in theory could be produced, 127 grams, and multiplied by 100 works out to be 82.7% yield. This is rounded to 3 significant figures. The final answer for this problem is 82.7% yield. Stoichiometry problems seem complicated at first, but get easier with practice. Don't forget that every stoichiometry problem begins with a balanced equation. The balanced equation for this problem reads as follows. 2 moles of potassium iodide plus 1 mole of lead 2 nitrate produces 2 moles of potassium nitrate and 1 mole of lead 2 iodide. There are 2 starting points for this problem, so this is a limiting reactant problem. We have to try them both. Starting with 50.0 milliliters of potassium iodide, I calculated that 5.19 grams of lead 2 iodide would be produced. And then starting with 75 milliliters of lead 2 nitrate, I predicted that 19.0 grams of lead 2 iodide would be produced. The theoretical yield would be 5.19 grams of lead 2 iodide, the lesser of the 2 predicted amounts. That would make potassium iodide the limiting reactant and lead 2 nitrate the excess reactant. Calculate the volume of 0.50 molar potassium iodide required to react completely with 50 milliliters of 0.50 molar lead 2 nitrate. So starting with 50 milliliters of 0.50 moles per liter potassium nitrate, I calculate that 0.10 liters of potassium iodide would be needed. Well, that's enough for now. We'll take a look at the answers for the nuclear chemical reactions next week.